Okay, in today's lecture, we'll talk about the next part of the section 5.1 material on sequences. So in the first part of the lecture, we had defined a sequence, or in particular an infinite sequence, as an ordered list of numbers. And these numbers are called the terms of our sequence. And we saw that these sequences can usually be defined by finding an expression for the nth term of our sequence, something of the form a sub n is a function of n. So in this next part of our section, we'll talk about another way to define sequences. So here we'll mention that sequences can also be defined recursively by using what is called a recurrence relation, or sometimes called a recursion. So as an example to illustrate a sequence that would be defined using a recursion or recursively, let's consider the following. So here we are told to consider the recursive sequence defined by the following. A sub n plus 1 is equal to 1 minus 1 over a sub n. And the first term of this sequence, a1, is defined to be 2. So for these recursive sequences, we're always given the first term of our sequence. In this case, a1, which is equal to 2. And this equation that we're given is called a recurrence relation, or a recursion. And what this recursion says is to get the next term in your sequence, that is a n plus 1, you're going to take 1 minus 1 over a sub n. That is, take 1 minus 1 over the current term that you have. So in this example, for that recursive sequence, we are asked to find our first 5 terms and determine whether our sequence converges. So for this example, we were given our first term of this recursive sequence as 2. a1 was equal to 2. Now, using our recursion to get the second term in our sequence, a2, we're supposed to take 1 minus 1 over the previous term. And a1 was equal to 2. So here we're taking 1 minus 1/2, which is 1/2. Now to get the next term in our sequence, a3, using the recursion, we take 1 minus 1 over the previous term, which we just found to be 1/2. So we're left with 1 minus 1 over 1/2 is 2, so we get -1. Now to get the next term in our sequence, a4, again we make use of the recursion. We have 1 minus 1 over the previous term, which we just found to be -1. So we're left with 1 plus 1, or 2. And to get our fifth term in this sequence, we would have 1 minus 1 over the previous term, which we just found to be 2. So 1 minus 1/2, or 1/2. Now at this stage, we notice a pattern emerging. So here, notice that the term that we found for a4 was 2. And that is the same value that we had for the first term of our sequence, a1. So it follows then that the next term that we had in our sequence, a2, or 1/2, would be the same as a5. So we see that this pattern is going to keep repeating. If we were to keep listing terms, our sixth term would be the same as a3, -1, and then a 7 would put us back at positive 2, and we keep oscillating through these same three numbers. So we've listed our first 5 terms, and the second part of this example asks us to determine whether this sequence converges or diverges. And we see here from listing out the first several terms that the terms in our sequence will keep repeating. So in this case, there is no one number which the terms of our sequence are approaching. So we would say that this sequence diverges by oscillation. There is no number or no single number which we ever are approaching. So let's look at another example of a recursive sequence, get a little more familiar with these. So in this next example, we are told to consider the recursive sequence defined by the following recurrence relation. To get a sub n plus 1, we take 2 times a sub n and subtract 3, and the first term in our sequence is 1. So again, we're supposed to write out the first 5 terms and determine whether our sequence converges. So starting with our first term, which we're given, we have a1 is equal to 1. Now to get the second term in our sequence, using the recursion, we're supposed to take 2 times the previous term, which was 1, and then subtract 3. So we have 2 minus 3, or negative 1. Now to get the next term, a3, we again apply our recursion. We have 2 times the previous term, which was negative 1, minus 3, which gives us negative 5. Then to get the fourth term, a4, we would take 2 times the previous term, which was negative 5, minus 3, which gives us negative 13. And then to get our fifth term, a5, we have 2 times the negative 13 minus 3, which leaves us with negative 29. And if we needed to, we could keep listing more terms. But based off the first 5 terms that we're seeing, it looks like the terms in our sequence are becoming larger and larger in the negative direction. So if we were to keep listing terms, it looks like the terms of our sequence are diverging to negative infinity. So again, this sequence defined recursively we see as diverging. Now, the next thing that we're going to talk about for sequences is some classification schemes for sequences. So we need to introduce a little bit of terminology here. The first type of sequence or first type of classification we'll talk about for a sequence is whether it is bounded or unbounded. So let's introduce some terminology here. We would say a sequence A sub n is bounded above if there exists some number, capital M, such that the terms of our sequence A sub n are always less than or equal to m for every value of n. So a sequence is called bounded above if there is some number m such that the terms of our sequence never lie above that number. And then similarly, a sequence is said to be bounded below if there exists some number capital N such that the terms of my sequence A sub n are always greater than or equal to capital N for every term in my sequence. And we would say that a sequence is called bounded if it is bounded both above and below. So when we're referring to a bounded sequence, we're talking about a sequence which is bounded above and below. Now, any sequence which is not bounded is called unbounded. So any sequence which is not bounded above or maybe not bounded below, is called an unbounded sequence. So let's look at some examples where we're given a sequence and we are asked to determine whether it is bounded or unbounded. So in our first example, part A, we have the sequence whose general term is 1 over n squared, going from n equals 1 to infinity. So in this example, we know that 1 over n squared is always going to be a positive number. So since I'm squaring the integer in my denominator, n squared I know is always positive, and so 1 over a positive number always has to be positive. So certainly the terms of my sequence are always greater than 0. And the terms of this sequence would always be less than or equal to 1. So why less than or equal to 1 in this case? Well, if we were to write out the first few terms of this sequence, starting with n equals 1, we would have 1. Then our second term would be 1 over 2 squared, or 1/4. Then 1 over 3 squared, 1/9. 1 over 4 squared, 1/16, and so on. So we see that the terms of our sequence are getting smaller and smaller as we list them. So the largest value that our sequence could take would be its first value of 1. So since we're finding that the terms of our sequence are always greater than 0 and less than or equal to 1, we can say the sequence is bounded. It is both bounded above and below. It is bounded below by 0 and above by 1. So since it is both bounded above and below, we say our sequence is bounded. So let's look at another one. In part B, we have 2n cubed over n squared plus 1. So for this example, we know that the terms of our sequence, 2n cubed over n squared plus 1, will always be greater than or equal to 1. Now why 1? Well, we can start to list the first few terms of our sequence. So if we were to start with n equals 1, we would have 2 over 2, which is 1. The next term in our sequence, if n equals 2, would be 16 over 5, which is greater than 1. Then the next term in our sequence, if n was 3, we would have 2 times 27, or 54, over 10, which is a little larger yet, and so on. So the smallest value that our sequence is going to take is its first value. It looks as we're increasing the value of n, the terms of our sequence seem to be getting larger. So we see that our sequence is bounded below by 1. Now let's think about whether it has an upper bound. So in this example, as we keep listing terms of our sequence, that is, as we allow n to approach infinity, let's look at the limit of our sequence, 2n cubed over n squared plus 1. So here we're looking at the infinite limit of a rational function, and we have a higher power of n in our numerator than we do for our denominator. So in this case, our numerator is growing more rapidly than the denominator. So as n keeps increasing, the value of this ratio is becoming unboundedly large, tending towards infinity. So there is no number that we would have for an upper bound. if we were to keep increasing the value of n, well, we can make the terms of this sequence as large as we want. So here, our sequence is bounded below, but not bounded. Remember, to be bounded, it has to be bounded both above and below. Now this one is bounded below by 1, but it has no upper bound. Therefore, it is not a bounded sequence. Now in our next one, part C, we have e to the negative n from n equals 0 to infinity. And we could rewrite this as 1 over e to the positive n, where n goes from 0 to infinity. So in this case, the general term of our sequence, 1 over e to the n, we know is always going to be positive, since an exponential function, e to the n, is always positive. Then 1 over that positive number must also be positive. And I claim that this sequence is bounded above by 1. To see why, we could list the first few terms of our sequence. So starting with n equals 0, we would have 1 over 1. Moving to n equals 1, we have 1 over e, 1 over e squared, 1 over e cubed, and so on for the terms of this sequence. And we see that these ratios are getting smaller. Therefore, the largest value of our sequence would be this first value of 1. So in this case, the sequence is bounded, since it has both an upper and lower bound. So boundedness is one classification of a sequence. We can classify a sequence as either being bounded or unbounded, or a little more specifically, perhaps bounded above or below. Now, the next classification that we'll talk about for sequences would be monotonicity. So in particular, whether a sequence is increasing or decreasing. So let's start with a little bit of terminology here. We would say that a sequence A sub n is said to be increasing if the value of A sub n plus 1 is always strictly greater than A sub n. So if the next term of our sequence is greater than the previous one, then it is called an increasing sequence. And similarly, our sequence is said to be decreasing if A sub n is strictly less than, if A sub n plus 1 is strictly less than A sub n for every term of our sequence. Now, we would say that a sequence is said to be monotonic or monotone if it is either increasing or decreasing. So any sequence which is either increasing or decreasing is said to be monotone. And if a sequence is neither increasing nor decreasing, it would be called a non-monotonic or non-monotone sequence. So let's look at some examples of determining monotonicity. In this next problem, we're given a sequence and we're asked to determine whether it is increasing, decreasing, or not monotonic. So in our first example, part A, we have the general term of our sequence is 1/3 to the nth power. Or if we prefer, we could maybe rewrite it as 1 over 3 to the n power. So I claim that this sequence will be a decreasing sequence, and let's see if we can establish why. So for these problems, sometimes it helps to write out maybe the first few terms. And if we're writing out our first several terms, Well, if n is 1, we would have 1/3. If n is 2, we've got 1/9. If n is 3, 1/27, then 1/81, and so on. So it appears that the terms of our sequence are decreasing, they're getting smaller. And to show that this is indeed a decreasing sequence, we could compare the term an plus 1 to the term a sub n. So here, a sub n plus 1 would be given by 1/3 to the n plus 1 power, which could be rewritten as 1/3 to the n times 3 to the first. Or we could think of this as 1/3 of 1/3 to the n power, which is 1/3 of a sub n. Now we know that 1/3 of a sub n is certainly less than 1 times a sub n. So we've established then that a sub n plus 1 will be less than a sub n no matter what the value of n. And that is exactly the definition of a decreasing sequence. So here a sub n is decreasing. So let's look at another one, maybe a little more complicated. In part B, we have a sub n is 1 minus 1/n squared. So it might help to write out the first few terms of our sequence. Starting with n equals 1, we would have 1 minus 1, or 0. If n is equal to 2, we would have 1 minus 1/4, so 3/4. If n was equal to 3, we would have 1 minus 1/9, or 8/9. If n is 4, we've got 1 minus 1/16, or 15/16, and so on. So when we list the first few terms of our sequence, it appears that it is increasing. So let's see if we can verify that it is indeed increasing. So one way to do this would be to compare the a sub n plus 1 term to the a n term. And here we would have 1 minus 1/n plus 1 quantity squared for our a sub n plus 1 term. And if we were to compare this with the term a sub n, well, this term would be larger than 1 minus 1/n squared. It's larger because we are subtracting a smaller value. If I were to increase my denominator from n squared to n plus 1 squared, that means that this fraction is smaller. So if I'm taking 1 minus a smaller value, that means I get something larger than what I had for my a n term. So we find that a sub n plus 1 is always greater than a sub n. So our sequence a sub n is increasing. Now, another approach, which we might use if we don't like this direct comparison approach, because it's a little bit messy in this example, would be to consider a calculus-based approach. So we recall from Calculus 1, in order to show that a function is increasing, we would need to show that its derivative is positive. So let's think about this general term of my sequence, a sub n, as being a function of n. Let's call it f of n. So if we define f of n as 1 minus 1/n squared, and we were to take our derivative of this function, f prime of n, we would have 2/n cubed. And as long as n is greater than or equal to 1, then this expression would be positive for all of the terms of our sequence, starting at 1 and moving forward. So if the derivative of a function is positive, that means the function itself is increasing, and this function is defining the term of my sequence. So another approach would be to differentiate the general term of your sequence, and if it's a positive value for the derivative, we can also say an is increasing. So let's look at another one. In our next example, part C, we have negative 2/3 to the nth power. So if we start listing out the first few terms of this sequence, starting with n equals 1, we would have negative 2/3. Then if n is equal to 2, we have a positive 4/9. If n is equal to 3, we would have a negative 8/27. And if n was 4, we have a positive 16/81. And we could keep listing terms. And because of the fact that we have this negative number inside of our power, we see that for each subsequent term, the sign is going to change. We'll always have a positive, a negative, a positive, and a negative. So in this case, our sequence is not monotonic. It is never increasing nor decreasing since the terms of our sequence are changing sign. So here our sequence is not monotone due to the oscillation. So any sequence which is oscillatory will be a non-monotonic sequence. All right, now to finish up with this section, we're going to look at a result which will determine whether a sequence is guaranteed to converge or not. And this result is called the Monotone convergence theorem, which says that every bounded and monotone sequence must be convergent. And to see why that would be the case, we could think about a geometric approach. Let's think about graphing the terms of a sequence. So if we were to look at graphing the terms a sub n of our sequence for different values of n, well, let's suppose that we have a bounded sequence. So here, if our sequence is bounded, that means that it must have both an upper bound, that is some number capital M, which we never fall above, and a lower bound, some number capital N, which the terms of our sequence never fall below. So if we have a bounded sequence which is also monotone, that is either increasing or decreasing, we're guaranteed it converges. So let's think about why. If we were to plot the terms of our sequence, let's say for a general discussion that it is increasing, so for n equals 0, 1, 2, 3, and so on, the terms of our sequence are increasing, but we know that they never lie above this upper bound capital M. Well, we see that as n is increasing, the terms of our sequence are converging to this upper bound n. Now similarly, if we were to have a decreasing sequence, if we keep listing our subsequent terms and they are getting smaller and smaller, but we are bounded below, there's some number that we can never fall below, we see that the terms of our sequence seem to be converging to this lower bound of n. So this sort of phenomenon is described by this monotone convergence theorem. If we have a bounded sequence which is monotone, we're guaranteed that it will be convergent. So let's look at an application making use of this monotone convergence theorem. Here we are told to consider the recursive sequence defined by the following recursion. So here a sub n plus 1 is equal to 12 over 8 minus a sub n, and a sub 1, the first term, is given as 4. Now in this problem, we are given that this sequence is both decreasing and bounded. So it is monotone and bounded, which means that it must converge by the monotone convergence theorem. So the problem is to then find the limit of that sequence. What is the value that it converges to? So let's start by saying that we are guaranteed the sequence will converge. So since we are told our sequence is decreasing and bounded by the monotone convergence theorem, the sequence a sub n converges to a limit of, let's call it maybe capital L for the limiting value of this sequence. So since we know it converges, the limit of this general term a sub n must be some number L. So let's think about how we can find the limiting value of our sequence. So here, if we consider our recursion, given by a sub n plus 1 is equal to 12 over 8 minus a sub n. If we were to take a limit on both sides of this recursion as n gets large, let's see what we have. So on the left-hand side, well, as n gets larger and larger, we were saying that the terms of our sequence, a sub n or a sub n plus 1, are approaching some limiting value of L. And on the right-hand side, taking the limit of this quotient, well, we have 12 over 8 minus, as n becomes large, we said the terms of our sequence a sub n are approaching some limiting value L. So we now have an algebraic equation which we can solve for L. If we multiply both sides through by an 8 minus L, we have the following. And distributing, we have 8L minus L squared is equal to 12. Or moving everything to the right-hand side, we have a positive L squared minus 8L plus 12 is equal to 0. And we can solve for L by factoring. So here this factors as L minus 2 times L minus 6, which has to equal to 0. So we have two options for our limiting value, either 2 or 6. And the question is, well, which one of these values is the limiting value of our sequence? Now, to answer that question, let's look at what we were told for this sequence. We were given our first term, a sub 1, is equal to 4, and we were given that the sequence is decreasing. So every term after the first term must be less than the previous one. Therefore, our limiting value could not possibly equal to 6, since every term which follows our first term of 4 must be less than 4. So our only choice then is for the limit of this sequence to equal 2. So let's look at one last example to illustrate this process for finding the limit of a recursive sequence. So in our last one, let's consider the sequence which is a recursive sequence, defined as a sub n plus 1 is equal to a sub n squared plus 2 over 2a sub n, where the first term of our sequence a1 is 3/2. And let's say that we are given this sequence a sub n is decreasing and bounded. So since it is decreasing and bounded, we know by the monotone convergence theorem the sequence a sub n is convergent with a limit which we will call L, capital L. So in order to find the limiting value of this recursive sequence, we can consider our recursion, which was a sub n plus 1 is equal to a sub n quantity squared plus 2 all over 2a sub n. So if we take a limit on both sides of this recursion as n becomes large, let's see what we have. On the left-hand side, the terms of our sequence a sub n or a sub n plus 1, as n gets larger and larger, we said are approaching some limiting value of L. Now on the right-hand side, taking our limit as n approaches infinity, we will have L squared plus 2 over 2 times L. So we now have this algebraic equation for L, and to solve, we could start by multiplying both sides by 2L, giving us 2L squared is equal to L squared plus 2. And then if I subtract an L squared from both sides, we have L squared equals 2. So our limiting value for L could be plus or minus the square root of 2. Now here we were told that our sequence is decreasing and bounded. And the first term of our sequence is 3/2. Now in this case, both of our values for L, plus or minus the square root of 2, are less than that initial value 3/2. So the fact that we have the first term and that this is a decreasing sequence doesn't give us any information about which of these values we should choose. But if we look at the recursion itself, if the first term of our sequence, A1, is positive, then if I'm looking at the next term of my sequence as a sub n squared plus 2, we know that numerator will be positive, and then 2 times a sub n, well, if a sub n is positive, then our denominator will also be positive, which means that every term of our sequence